Okay, so this is going to be the first of our last series of videos. These are the videos on eigenvalues and eigenvectors. Before we jump into the topic of eigenvalues and eigenvectors, I want to start with one video kind of overviewing one of the sort of geometric scenarios where this idea arises, and this is one of the places where this sort of problem originally comes up. And so the problem is, we're considering matrix transformations. So remember, this is, we're looking at things like, like y equals a times x, where a is a matrix. And so this might be something like, say a 2 by 2 matrix. So y1, y2 looks like a, b, c, d times x1 and x2, right? So one vector goes in, the vector x goes in, right? So we think of y as being a function of x here, right? Your function t is your matrix transformation. And so you put one vector in, you get another vector out. And most of the time, it's not so easy. I mean, you can compute it, but just looking at the numbers in the matrix, just by looking at these numbers and then looking at the vector that you're putting in, it's hard to kind of predict by looking at things how the magnitude and direction of the output is going to be related to the magnitude and the direction of the input, right? And even in some cases, some vectors are going to get stretched, others will get shrunk. Some will be rotated one way, some will be rotated another way. There's a lot that can happen even in the 2 by 2 case. If you go back and you look at the section on transformations of the plane, you can, even with just a simple 2 by 2 matrix, you can come up with some fairly complicated looking things. And so one of the things that you're interested in when you're studying these is, are there certain vectors that you put in so that the output is parallel to the input, so that maybe the magnitude changes but not the direction? And so basically, the idea is that you put in, your vector, so x goes in, and then you calculate t of x, and you find that t of x lies along the same line. And so one of the things that happens is that because you know that t of any scalar multiple of x is so one of the properties for a matrix transformation is that you can pull out scalars, right? That means that anything in the same direction as x, so any multiple of x is going to get sent to something which is parallel to x, right? And so one way to think about it is that this entire line, if you like, this entire subspace is preserved. And so one of the things that you would study in a more abstract course in linear algebra is you might, if you're studying linear transformations on a vector space, you might be interested in those subspaces of that vector space that get left alone by the linear transformation, in the sense that every vector from that subspace gets sent to another vector in that subspace and not to something outside the subspace, right? So not to some vector which lies off of the line. And there are a lot of problems in a lot of different areas of mathematics that can be studied in this context of subspaces that are preserved by linear transformations. And so before you can really understand that problem, you have to first understand this sort of concrete problem of eigenvalues and eigenvectors. So just to give you an idea of how this might work, right? We know, so we've already kind of reviewed this, right? Sorry, that should be a little x there. So we know that if a matrix transformation, you take one vector, a little x, you multiply by the matrix A, you get out another vector y. We can think of this as a function. And so there are a number of kind of specific geometric sort of operations that can be expressed in this way, right? So here, one example we have here is a rotation, right? So this matrix that I've written down is the rotation matrix, and this I think the minus sign should be in the other spot. Well, okay, it's a clockwise rotation. So this is a rotation matrix, and so this is one where, well, if we're looking for vectors that end up parallel to themselves, you're not going to find any, right? Because what happens? You start with a vector x. Here's x, right? And you rotate through some angle, and so your output, t of x, or a times x, right, is over here, and it's given by rotation through some angle of theta, right? And so every vector is going to be rotated by the same amount, and so there's no vector that's going to end up parallel to itself unless theta is a multiple of pi. Well, I guess there's one vector that ends up parallel to itself. That's the zero vector, but the zero vector doesn't have a direction, right? We're interested in non-zero vectors that end up parallel to themselves, and so this is an example of a transformation where nothing ends up parallel to itself, right? So there are no invariant directions. There are no directions that are preserved. On the other hand, if you go with a multiplication operator, so this sort of operator which just takes a vector and multiplies by a scalar, I mean, you can think of that as a matrix transformation, because multiplying by the scalar lambda is the same thing as multiplying by lambda times the identity, right? Now, in this case, every vector ends up parallel to itself, right? By definition, a scalar multiple of a vector is parallel to the original vector. So we have kind of two extremes here. In the first example, every vector ends up parallel to, or sorry, no vector ends up parallel to itself in the rotation example. In the multiplication example, every vector ends up parallel to itself. But there are lots of intermediate scenarios where some vectors end up parallel to themselves and others don't. Okay. Here's one example. This is a shear transformation. So this is a vector which, this is a transformation which, if we were to graph this thing, okay, so a vector. If I put in the vector, so here's sort of 1, 0. Okay, and if I calculate f of 1, 0, so you can calculate f of 1, 0, okay, 1, 1, 0, 1 times 1, 0, that's going to be, well, 1, 0, okay? So this one is left alone. It gets sent to itself. So this kind of horizontal direction, and in fact, if I put in any kind of, if I replace that 1 by a k, right, you can see that I still get the same thing out, right? So any vector parallel to the x-axis gets left alone. It ends up, you get the same thing out that you put in. On the other hand, if I put in the vector 0, 1, well, you can check that when you do 0, 1, what do you get? Well, you get 1, 1, right? So this vector ends up, so this is there, but 1, 0 gets sent to this guy, right? Which is definitely not parallel to what you put in. So this kind of, this ends up over here. So that vector gets kind of shifted over, right? So this shear, it's a horizontal shear, so any vector with a vertical component is going to get shifted over to the side a little bit, right? So in this case, you have one direction which is left alone. You have another direction which gets moved, and you can play around with this, and you could find that, in fact, the horizontal direction for this particular example, this horizontal direction is the only one that's left alone. So what we're going to do in the next couple of videos is we're going to develop computational techniques that will let us figure out which directions are preserved looking only at these numbers in the matrix. So we'll be able to look at those numbers, do some computations, and figure out what are sort of these invariant directions that get left alone by the transformations, and of course every other direction is something that's going to get moved around when we apply the transformation. So we'll look at those in the next couple of videos.